Thanks, everyone. I want to start with a question. So raise your hand if you have heard of WebAssembly before. Keep your hand raised if you have used it, done something with it. Okay, cool. That's like a very steep drop off. That's great. This is why you're here. I want to give a talk today about WebAssembly, but not just sort of like the surface level pieces of WebAssembly. I want to kind of go deep into what it actually means when you have these instructions executing. But this is a JavaScript conference, and so the perspective I'm coming at this from is a year ago, I knew some things about WebAssembly that were mostly folklore. So I knew it was fast. I knew it was a successor to an idea where you compile JavaScript to a single array of numbers. That's fine. I knew it had many use cases purportedly for things I did not really do in my job, including graphics like physics engines, rendering, computing very large Fibonacci numbers. That's in all of the demos too. I knew that it was formally specified and verified, and as a programming languages person, this was very exciting to me. We'll get to more of that later. And I had heard from some people who didn't really know anything about JavaScript or WebAssembly that WebAssembly was going to replace JavaScript, so that was potentially a cause for concern. I want to give you some context for why these specific things were my preconceived notions. I am kind of an academic and researcher first, and a software engineer second. Software engineering is my day job. I work at a startup called Notion. We build a computing toolkit that pretends to be productivity software. It's great. Before that, I worked at Khan Academy. So basically, I'm an extremely professional JavaScript developer. I write JavaScript for a living and React, and just like all of you. By night, I basically just read papers about the lambda calculus. So I research programming languages as user interfaces, specifically what it means for even just text-based programming languages to present a good or bad user experience. I'm really interested in functional programming, rich type systems, Rust, Haskell, things like that. I did an undergrad in computer science. I was supposed to take operating systems. I did not take operating systems. Instead, I took a type theory class, which is just an entire quarter of just the lambda calculus. So that's where I'm coming from. And so there are two kinds of WebAssembly talks. One kind sort of does the surface. By the way, you're really procrastinating on your slides when you paint a cross-section schematic of the levels of the ocean. Okay, so I texted Jordan Scales this 2 days before. I was here's how my slides are going. As you can tell, we're on slide 5. Okay. So there are two kinds of talks, right? One is the surface level talk that gives you sort of the overview of here are the things you can do with WebAssembly that may or may not be relevant to you. Here are the compilers and stuff like that. This is not that talk, as you may have guessed from sort of everything that led up to this. I want to go deep into WebAssembly, and I want to sort of unmask the black box. And the question is sort of why would you choose to do this in a talk? And to do that, I will ask another question, which is how many times have you encountered a technology and thought to yourselves, wow, this seems really cool, except I am a React developer, and so I will only gain a cursory understanding of this, smile, nod, and move on, and not actually know what to do. This is me most weeks, actually, even though I'm an academic. A few examples of this. Algebraic data types, very common in functional programming languages like Haskell, OCaml. At one point I was man, I don't do any of these things, kind of with the calculus thing, I was really bad at Newtonian calculus, terrible. Spectre and Meltdown, my relatives were should I be concerned about this? I was I don't know, Twitter says so. Containers, I asked my coworker the last week, I was I ran Docker Compose up, does that make me, a qualified cloud computing professional? They were the cloud is just someone else's computer. I was oh man. All right, okay, so the point is, right, I was like this once, right? These are all actual quotes from me in the past maybe 18 months, and now I'm up here giving this talk. And so I want to kind of take you through words that you see them and you're wow, those are words, and unpack what that actually means. So to give you an example of words, this is what it says on the WebAssembly website. It says WebAssembly, abbreviated WASM, which I find really awkward, so I'm not going to really say it, is a binary instruction format for a stack-based virtual machine. The first time I read this, I was well, that's really cool. Those are words. And then I kept reading, and it was WASM is designed as a portable target for compilation of high-level languages like C++, and Rust. And I was oh yes, C, my favorite high-level programming language. I'm right there with you all. So then the question is like, why does WebAssembly matter? So I don't really need to rehash these first 2 bullet points because your non-JavaScript colleagues have probably tell you this every day, which is that we need a performant runtime for the web, and it was designed by accident in like 10 days, and now we're stuck with it forever, and it was only supposed to do like, cursor animations, but now we're trying to like write Facebook with it, et cetera, et cetera. I don't really want to go over that. But sort of more importantly, right, as a developer, you might want to do things like, Josh's cool animations or like other cool physics simulations or rendering or something like that. And the truth is that there are a lot of existing native libraries in like C, C++, and all of that that have already been written to do things like linear algebra, simulations, whatever. And it would be really nice if we as front-end developers could just seamlessly interoperate with those libraries as simply as like calling a JavaScript function. And people recognize this. People have recognized this for a really long time. So there are a lot of prior systems, like Microsoft had ActiveX, Chromium has native client or NACL, there is ASM.js, which a lot of you have probably at least heard of. And these are all systems that aim to provide native performance in a web environment. But the reason WebAssembly is so significant is because all of these prior systems, 3 and many others, don't achieve all of WebAssembly's design goals, which can be roughly divided into 2 categories. 1, how does the language look, how is it represented, and 2, how does it run? So the ones I want to pick out here in terms of like the representation, we want, on the web, right, we want things to be very compact so that you don't have to send, your 95 megabyte bundle down the wire, and we want it to be easy to validate and compile in a single pass. This is like how web browsers wanted CSS to be a single pass algorithm rather than a constraint-based solving system, because that makes it fast to render. And then in terms of how does it run, the main thing I want to focus on besides speed is safety. So you may have heard like, C and C++ people complaining about like buffer overflows, memory leaks, memory unsafety. The whole sort of reason we have Rust is because of memory unsafety. And so the key idea here is that when you have machine level code and it is operating in some context and you can like just change the pointer to like the next place in the call stack to just point to like your other call stack where you injected malicious Bitcoin miners or whatever. That's very dangerous. It's like it's pretty much like a lawless land. It's a total disaster for security. But this is very important for the web, right? And then portability is important because the promise of the web is sort of this universal application runtime. Everyone has a web browser. They can install it. They can like run your application using it. And if you're suddenly like, well, if you want to run my web application, I really need you to install LLVM and CMake and then sit here through like this like 15-minute CMake installation before it tells you that like homebrew symlinked your user local folder to the wrong place. Like that's sort of breaking the promise of like the web as the universal runtime. So portability is very important. Okay, and this all comes from this paper called Bringing the Web Up to Speed with WebAssembly, which was done by a lot of people who were part of the WebAssembly working group. It's kind of dense, but I would really recommend it, and there will be links to it at the end. Okay, so this is the part that I want to focus on, and this sort of frames the talk. This is a quote from the paper, and it says, "To our knowledge, WebAssembly is the first industrial-strength language or virtual machine that has been designed with the formal semantics from the start." So keep in mind that. What does that mean? This not only demonstrates the real-world feasibility, I hear the React Rally conference is all about real-world feasibility, of such an approach, but also that it leads to a notably clean design. And so what I want to talk about sort of in this talk is how WebAssembly works. But the thing I want you to be thinking about in the back of your mind is how is this easy to understand? How might this be easy to reason about? And how are these features or user interface components of a programming language influenced by the upfront design decisions to do something from first principles and very clear sort of design goals, rather than sort of coming at it from like a ad hoc approach and just tacking on pieces as the use case arises. Okay? Cool, so some high-level things. WebAssembly is typed. There are 4 types right now, along with 4 primitive types with functions, and there are more coming. There are 32 and 64-bit integers and floats. This talk will only use 32-bit integers. You can basically just think of it as a number. Linear memory. So remember how I said before it's like kind of sketchy if your program can just like change the memory of other programs. So WebAssembly modules are each executed with their own contiguous sequence of memory. This is completely disjoint from the memory that the code lives in and the memory that the execution stack uses. And so this basically means that at worst, a WebAssembly module can corrupt its own memory, but it cannot corrupt its host environment or other software modules, and that's really important. And lastly is structured control flow. So those of you who have seen sort of assembly-like languages, you know it's kind of just like you read straight down and sometimes it's like jump, and you like jump. And it's like you can jump anywhere, and then, you know, if you had to go through like an undergrad CS program and do systems, they were probably like figure out how this recursive function, which has been compiled to regular assembly, like is implemented. You're like, this is terrible. So WebAssembly is like, no, none of that. Instead, they have structured control flow, so that means you get constructs like loops and blocks that we're used to having in JavaScript in this like low-level language, and there's very clear semantics, which is sort of like what it means to execute a loop and how you can rewrite that. So this is sort of like bringing some of the higher-level comforts that we're used to as JavaScript programmers to the WebAssembly context. Okay, starting with these bold words from like that description of the language earlier. A compilation target for high-level languages like C, C++, and Rust. I'm going to have great faith that even people who have not written C++ before can figure out what this does. It returns an int, and it takes an int, and it specifically returns like that int +1. Okay, that's great. And so how would this function get compiled to WebAssembly? Well, the first thing, does my laser pointer work? Okay, cool. Does it work here? Yeah. So here you just get this label, which says it's a function 0. It has one parameter called var0, which is a 32-bit integer, and then the result is a 32-bit integer too. And then there's some instructions in the body, which we will get to later. But you can sort of like understand the structure of a function. This is like WebAssembly text format, by the way, so it is canonical. And then let's say we have two functions, right? So you want to compile this into a module. This is a very straightforward module. It's just the add1 function from earlier. And then in addition, we have the main function that takes its argument and passes it to add1 and just returns that result. So it's just like a layer of function indirection. Okay, cool. So this gets compiled to a module that looks like this, and I don't need you to like read this, but just to see that this is really like the text representation of the entire WebAssembly module, including the memory initialization, the upfront declarations, any exports, etc. So it really does like kind of fit compactly and not too overwhelmingly, like in a single slide. And that's sort of what I want to impress upon you just from this slide in general. Okay, it said it was a stack-based virtual machine. This basically means how does it run? If you took like an English class where your teacher told you there's syntax and semantics in the English language, the same principles kind of apply to programming languages. So syntax is like the structure of the language, how does it look, how is it set up, how is it represented. Semantics is what it means, how it runs. You could take two languages that look exactly like JavaScript and just arbitrarily say that in one of them, every time you call a function, you have to deep copy all the arguments. Like it would be, you know, silly, but like that is a decision one could make. And that's sort of the semantic syntax difference. Oh, sorry, I'm like standing in front of, cool, okay. So for the stack machine, to explain this, I want to use the example, which is just the WebAssembly translation of the module that we had earlier. So that is the first top function just adds 1, and the bottom function takes its argument and passes it to add 1. So the first thing that we have is this like main function, and the first instruction says to get local. So this is in WebAssembly how you reference a local variable. And on the right, I have this illustration of the stack. So we have var0, and we just put it on the stack because the semantics of get local is that you start with this empty stack, you take this local variable value, and you stick it on the stack. Then you have to call this function. And so remember how I said earlier that WebAssembly was typed? So what this means here is you look at the function signature for the thing you're trying to call, and you say, okay, it takes one argument, and it returns one argument. And so what you do with that is you say, okay, it takes one argument, so you pop that many things off the stack. We used to have var0, and now we don't have any. And you create a new stack frame that's sort of like a substack that is going to represent execution of this helper function. You can see here that I have this 1 in var0 thing. That's because the stack frame is indexed by two values. First is the number of return values for the function, which is 1, and second is the locals that function has access to. You can think of this as a representation of like a closure in JavaScript where you can close over environment variables and still access those. How would the compiler represent like the closure internally? Well, you can't just have like the function text. You also need references to everything from the environment that you got passed. Okay, so now we're inside this function, and we've pushed sort of the arguments onto the stack. And the first thing we need to do is get a local variable, which is the argument, because we're adding 1 to it. And we've already seen how to get a local, so that's there. And the next thing we do is just have a constant. So the const instruction says it takes like an integer and it just like sticks that integer on the stack as well. So this is what our stack looks like. And finally, we get to addition. So we have these two things on the stack. Now we need to add them. And just like we had earlier a function that had a type signature, every instruction in WebAssembly also has a type signature. So you can just look this up in the reference manual and see, okay, add, and I accidentally have taken the floating point ones, but just pretend it says integer and I. If the signature is, it takes two 32-bit arguments and returns a single 32-bit argument. And so that's what we do here. We pop two things off. So earlier we had 1 and var 0, so we pop two arguments off, and we push the output on, okay? And then, now that we're done sort of executing this function, we just return to the caller. We say, okay, this stack frame was supposed to return one thing, so you pop that many things off of this, and you just push it on the parent stack. Does that kind of make sense to people as to how execution works? Cool. Okay. So that is all that is meant by a stack machine. It's just like how you want to run the function, how you actually go about interpreting each of the instructions individually. And so now you're like, okay, we are halfway through this talk. This is React Rally, and there has been no JavaScript. I was promised JavaScript. To which I will say, okay, yeah, that's fair. So we can do some JavaScript. It is actually really easy to load a WASM file. It's just these 3 lines. There's actually a new API called instantiate streaming, but I couldn't get it to work, and so that's 1 line, but this is 3, so it's like not that bad. Classic academia, right? Okay, and so to demonstrate this, I will say, copy this into the console. Oh no, that copied way more things. The cursor reveal JS. And then we'll say window.demo equals module and instance here. So all this does is it fetches this WASM binary that I've precompiled. Actually, it is, how I compiled this, I went to WebAssembly Explorer. I typed this C++ into the left. I hit compile. I clicked download, and I saved it to my talks folder. So this is how you can get started with this too without installing like mscripton or binarian or any of those other compiler things. Okay, so, and this is just the thing that I downloaded from the website. So now I have window.demo, and you can inspect the exports. So demo.instance.exports shows you, okay, there's add1. The symbol's been kind of mangled by the C application binary interface. But then there's main, and then there's memory, okay? And these are just like the functions that I defined from C++ that were compiled to WebAssembly. And not only can I inspect them, you can call them. So demo.instance.exports._z6 add1i of 2019 gives you 2020, and for like 0, it gives you 1, and so on and so forth. So that's pretty cool. That's like literally all there is to creating and calling a WebAssembly function in JavaScript. You go to this nice fiddle website, you write like really basic C++ that you copied from C++ in 30 minutes, and you like call this function. You write these 3 lines of JavaScript with a fetch call, and you call this function. That's like actually all there is. Cool. So I'm going to tell you a little bit about a project that I immediately did with a friend as soon as I learned like those basic things right just then. I can hide the console for now. So this is my roommate, Meg. We all really like systems programming and static analysis, and we were kind of just like sitting around one day, around a year ago, doing Girl Talk. And for those of you who are unfamiliar, Girl Talk is when women get together and discuss topics like how to, instrument precompiled static binaries to inject arbitrary code. And so. So we were like, okay, we want to do this project in Rust. We don't really have any idea what to do. And the solution to this is always to ask Mozilla people what to do. So, so we talked to Nick Fitzgerald and Jim Blandy, who are at Mozilla working on the Firefox debugger project. And Nick's idea was basically something called Dtrace for WebAssembly. So in JavaScript, I'm sure all of you are intimately familiar with the experience of not knowing what's going on. So you just type like console log hyphen, 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 and you're like, ah, yes, my function has not been called, and I have no idea where the bug is. WebAssembly programmers are not afforded such a luxury, and certainly a year ago, if you wanted to call like a native JavaScript or DOM function from WebAssembly, that was pretty expensive. It was like the cost of crossing the foreign function interface. And so what we basically wanted to do is say, okay, you have this Rust function on the left. This was in Rust, by the way. And it's, it's in Rust, but it's pretty standard. You want to call this function, do stuff with for. And then on the right, you just want to see like this like console log that's like, we called this function, then we called this function, and it returned this thing, so on and so forth. Very straightforward. But they wanted to basically say, take a Rust source program, compile it to WebAssembly, do some stuff, like mess up the binary instructions in that WebAssembly module, and now when you run that messed up one in the browser, you can somehow use JavaScript to like access this information. So how to do this is like not immediately clear. But I want to walk you through kind of like the high level, the source code for this is on GitHub, there will be a link at the end, but I want to walk you through sort of the high level approach that we took and some of the things that were tricky about this when, keep in mind, we did not know WebAssembly at the start of this project. We were kind of just learning it on the go, like IRC, like Rust beginners, like frantic Nick, please help, I have corrupted my call stack and I write JavaScript, so I don't know how to fix seg faults. Okay, great. So start with the Rust program. Rust on the left, JavaScript on the right. They are pretty similar. So you can sort of just, I've only added JavaScript just to demonstrate how similar they are. You have add1 and main, which instead of calling add1 directly, calls add1 twice. This is just to make the example interesting at all. So okay, I said Rust and JavaScript are very similar. I was like a little bit lying because you look at this and you're probably like question mark. So this is the part where you allocate global memory in the module. And the JavaScript's like rough approximation is you have this kind of global, and it's called tracer. And let's say it's some number of bytes, but it's just an array in JavaScript. And we have this function called expose tracer. In JavaScript, you just pass around, if you return an object or an array, it just gives you a reference to that object on the heap. But in lower level languages, you want to explicitly pass a pointer. So what you have in the first example, in the Rust example, is the code will actually pass you a memory address. And we'll see this in JavaScript in a second. It's like an actual number that you use to index into linear memory. And then you compile the Rust program to a WebAssembly module. You can use like the Rust compiler, or you can use any of these like nice online fiddles that I prefer to use to avoid installing things on my computer. And then remember this module layout that I put up briefly earlier? So one thing it has is the ability to see all of the functions that are in the module. So if you know the binary encoding, which I didn't, but someone who wrote a Rust package did, you can sort of like take in a WASM module and then iterate over the functions before anything is being executed and sort of instrument the instructions inside. So the first thing we need to do is add a prologue to add prologue instructions to say, okay, hello, I'm a function and I'm being called. And so what this looks like here, if you remember back to the execution semantics we just talked through, we say, okay, push the ID of the current function, so in this case it's 0, onto the stack. Then we have this log function call thing, call that. That will take the ID, pop it off, write it to the global memory we allocated earlier, and then just like move on with the rest of the function. Does this seem pretty clear? We literally only add like a few instructions. Okay. The question now is, how do we write the return value to memory? So this is sort of the body of the function, and that's what the stack looks like when we're done executing. And the thing that's a little bit tricky is that even if we have a function called log return value, we can't just call log return value after this, because if you recall, log return value will pop the result off the stack, okay? And now it's gone. And when the normal function tries to return, you are screwed because it's supposed to return one argument, but you don't have anything, and this is how your module gets very sad. So this is an invalid state. WebAssembly is all about not having those, and so we need to figure out what to do. And so the solution is this instruction called tlocal. It was a little confusing to me at first, so I wrote like actually what this single line means in JavaScript. So tlocal basically copies the top of the stack, not like pops, just copies it to a local variable that you can now just like have as a reference later. So if the stack has var 0 plus 1, our final result, tlocal is like saying pop the stack, assign that to a temporary variable, now it's empty. Take your return value local that you've declared earlier and say temp is now, assign temp to it. Push temp back onto the stack, but now you have this return value thing that's kind of just hanging around, and you can do something with it, like call get local. And so now you have 2 copies of the return value on the stack, and with that, you can just say, okay, log function return, This will pop the top one off that we just added, create the log function return stack frame, which doesn't have any, it's a void function, and we still have that var0 + 1 result, which means that when the regular function returns, it's still legal. So the final epilogue is just these 3 lines. It's a little more complicated in practice, but it really is sort of, these 3 lines are like the core of it. And so, okay, now I'm going to show you something that's really cool, which is the same lines of WASM, or the same lines of JavaScript to import WASM, but we have the module and the instance which correspond to a different binary. This is an example of an output Rust binary that we instrumented using our program. So, same way as before, instance.exports.negate10. You get -10, which is what you would expect. This is the cool part. So, instance.exports has this thing called memory. And memory is a webassembly.memory that contains an array buffer. And this array buffer itself will let you, basically, it's like very long, because the really tragic thing is that Rust compiles like the entire Rust standard library into the module as well. So it's like, that's why I'm not showing you the actual module, because there's like a zillion things you don't care about. I think this has gotten better. This is old code. But so if we copy this code in, you can see here this int32 array has 0, 72, 2, and -10 in it. This is really cool because you are actually looking at the linear memory of like 32-bit integers that is visible to the WebAssembly module. And in particular, this is the global tracer that we allocated earlier that contains 4 entries. The first is a 0, which is part of the enum that says, okay, I said a 0 is going to be a function call, a 1 is a void return, and a 2 is a return with a value, okay? So 0 says we're a function call, 72 is the ID of the function because we had 71 standard library functions before it apparently. 2 says we returned, and -10 says we returned -10, okay? So if we say, if we say like negate, 4 or something like that, and we look at the buff again, you can see that it has 0, 72, 2, -10, and a new 0, 72, 2, and -4. So as we sort of like call functions in WebAssembly, you can use JavaScript directly with a typed array view to inspect the contents of the memory that is visible to the module and that the module can write to. I think this is really awesome because it sort of gives you a way to like, introspect the operations of native code, basically. And a way to sort of like instrument native code in a way that will allow you to inspect it from JavaScript later on. And so, and this is like all as simple as just like, there's very little code other than what I'm showing you up here. Okay, cool. So, soundness. I finished all of that and I have like n minutes left, so that means I get to talk about soundness. WebAssembly is cool because it is sound. Remember how I said there was a verified semantics earlier, okay? So that gives you 2 things. It gives you type safety, which says you won't have invalid function calls or instruction calls because instructions are typed as well. And you will never access locals that you're not supposed to, which is the basis of a lot of security vulnerabilities. Second is you get memory safety, which says you don't get buffer overflows, which for a really long time, I didn't know what buffer overflows were, but like I had looked at the Wikipedia article and it said that there was like a hack in Zelda that let you name your horse something, which like caused a buffer overflow. So just think of it as that. You can't rename your horse, but it's still good otherwise that you can't have those. No dangling pointers. Dangling pointers are like in C, you can have an array and you can like, this array might be like 20 elements long, but you're like, give me, 2,000 and oh wait, that just happened to be like where all your passwords were stored in memory, like my bad. Can't do that. The code and the call stack are not accessible to the program, which is what I described earlier. Okay, how do we do this? Don't read this slide, just look at it. Don't read it, just look at it, okay? There are typing rules that tell you that each instruction will always produce sort of a valid, if you give an instruction valid inputs, it will produce valid outputs. And then for modules as a whole, there are a few more typing rules, okay? This is how you sort of validate that a WebAssembly module is correct. And when you look at this, you're like, this is a lot. To which I would respond, the corresponding verification for Java bytecode, or for ensuring that like Java modules are well defined, is 150 pages of the JVM specification, okay? And so I will take one like very illegible half slide over 150 pages any day. And this is like shockingly impressive because if you think about it, there's nothing about, okay, actually I didn't mention this, but new fact, there is nothing about WebAssembly that requires it to be on the web or in browsers or have to do with JavaScript. It is actually a portable binary format. And so in the same way as you can take, you can write JVM programs in like Scala or Java or, Clojure or anything like that, compile it to this bytecode and have it run, you can do the same thing with Rust, C, C++, Haskell, all these, other languages that are like, oh, we can compile to WebAssembly now. And it is still like a universal runtime for these. And so that's really cool that you can verify that one of these modules is correct in such a small, with so few rules, basically. Okay, so coming back to this, formal semantics. Validation, which happens before any WebAssembly module is compiled in the JavaScript API, says that the code cannot exhibit any undefined behavior. Undefined behavior is like how you have web browsers that sometimes just have like wildly different and creative interpretations of what certain Flexbox properties do, except instead of like Flexbox properties, this is like how your machine like manages low-level memory next to your password memory, which could be like potentially more bad for it to be undefined. And so having these guarantees allows you to say, okay, we have this execution environment for the web, and we know that it's not going to misbehave. It's also fast, it's portable, and this is all achieved compared to like prior art because people were like, we're going to design this from first principles. Cool. So there's a lot of things you can read. The slides for this, I'll link them in Slack, but they'll be on my website. The reference manual is this like really nice plain English description of the WebAssembly semantics that is derived from the formal specification. The Explorer is the fiddle I showed you earlier that lets you write like bad C++ and compile it to WebAssembly just for the purpose of playing around. And then there are these 3 design docs, which are like GitHub gist type things that I read a lot of to understand sort of how WebAssembly worked. I want to thank my roommate Meg. Jesse was our advisor for this project, and then the two, Nick and Jim from Mozilla, like helped us every time we totally borked Rust. So this was super awesome. You should talk to me on the internet. I have a Twitter. The Soylent is about, it's like Soylent Green the movie. I've never had Soylent, and I don't, it's not that Soylent. It's got co-opted. That's the GitHub repo, which is the Rust code, and a bunch of JavaScript examples for the thing that I was showing you earlier. I work for a company called Notion. It is very nice. We are hiring. We use React. There are 8 engineers, so you get to hang out with me all the time and do like weird stuff. Like, we don't do WebAssembly at work, but we can do weird React stuff. It'll be just as fun. And you can look at our jobs there, and I'm happy to talk to you about it afterwards. That's all I got. Thank you all so much.